The mass of Jupiter all by itself is more than twice the mass of all the other planets combined. And yet we know hardly anything about it. When we look at it, what we're really seeing is the tops of the clouds. We don't know that much about what's underneath. We see gas, we see these belts and zones, jet streams moving at 1,000 kilometers an hour or something, and we don't know how deep they go. We see a storm more than twice as big as the whole Earth, and we don't know how deep that goes. We have a general idea of what powers it, but there's all kinds of stuff we don't know about it. It has the strongest magnetic field in the solar system of any planet, extending out way beyond the planet, and we don't know the details of how that's generated. The pressure's so high, the temperature's high, the conditions are so intense that it looks like there's this huge ocean of liquid metallic hydrogen inside Jupiter. You have to go down to where the pressure is like 2 million times the pressure here on the Earth, which is maybe a third of the way towards the center of Jupiter. The magnetic field that we see on Jupiter comes from that ocean of liquid metallic hydrogen. And in fact, that's the main way we know that liquid metallic hydrogen even exists. We see this giant magnetic field, and our only plausible explanation for that magnetic field, which must have an ocean of swirling liquid metal to generate it, is that ocean of liquid metal is liquid metallic hydrogen. So by measuring the magnetic field and understanding where it comes from and understanding the pressure and the density inside Jupiter, one of the things we can do is get at fundamental properties of the simplest element there is, of hydrogen, and try to understand its equation of state.
There's different ways to explore planets. Typically the first time you go, you'll do equatorial orbits, so you can study the moons and the whole system. But if you want to do a close-in study of a planet, you typically want to do what we do at Earth. You do polar orbits.
Basically, we have not ever flown over the poles of Jupiter, so we don't have good pictures. When you look at the globe of Jupiter, we have great detail down in the equatorial regions, and then it's blurry up at the poles. That's because we don't have that data. Juno's coming in on a polar orbit over the pole of the planet, cutting inside the radiation belts really close, and then going out for a long time, for 14 days, and do it again over and over. What that lets us do is carry an innovative suite of instruments very close to the planet in a place where no one's ever put instruments before. One of the things that really makes the Juno mission special is our orbit takes us incredibly close to the planet. We're going to be skimming the cloud tops, measuring not just the visible pictures, but the ultraviolet and the infrared, and using radio waves to see inside the atmosphere, measuring the magnetic field from a hair's breadth away from the planet, measuring the gravity from right skimming above the cloud tops. All of those things, by coming really close to the planet, we can do a much better job of studying Jupiter and its interior than we could if we stayed 3, 4, 5, or 6 Jovian radii away from the planet, outside the radiation belts. So it's really key that we're going to dive inside the radiation belts instead of staying outside of them. Obviously, we can't fly right through the radiation belts continuously because we would fry all the electronics on the spacecraft. So the choice is, do you stay outside, or do you try and thread the needle in between and come inside the radiation belts? Juno, for the first time, is going to try to thread that needle, and therefore we can get really close to Jupiter.